between ions, isotopes, and just neutral atoms. Today we're going to do something. You'll see a few problems like this. There's a few problems in active about it. There's probably going to be a problem or two on the test that will relate to this. But we're looking at how we arrive at the number for the average atomic mass. All right, so it's just looking at basically it's calculating a weighted average, just like if you were to calculate your grade in this class, knowing that formative grades are worth 40%, summative grades are worth 60%, and you average them out and get the weight and put it in there. That's going to be the same type of calculation we're doing. It's not a type of calculation you haven't seen before. It's just using atomic masses and isotopes rather than grades and things like that. We're also going to start looking at particular regions of the periodic table. So you get to color a little bit today at some point. And so we'll have that. All right. So ending where we ended on the notes yesterday. We should have came up to right about this point. I think this is the slide that I left off of, or maybe the slide before. But basically, one of the things that I need us to know, so the mass number, the number that's written in red at the bottom of the periodic, bottom of each element box on here, that number is a representation of the number of protons and neutrons combined. So it's the sum of the number of protons and neutrons. So mass number for an isotope, an individual isotope mass number is the protons plus the neutrons. And same thing, yesterday we were seeing that we can calculate the number of neutrons if we have the mass and we know the atomic number, then we can determine how many neutrons there are. So the other thing that we saw yesterday is that there are different isotopes of elements. So going into this, the way that chemists over the years have come up with and settled on the number that carbon's average atomic mass is 12.0108 is because we have done experimentation on it over and over and over again, and we've taken the average based off of the different isotopes that we've discovered. So the way that we get there is by calculating a weighted average. A weighted average is always based off of percent. So I'm going to pull up the equation and try to put it into a reality-based situation. So atomic mass is equal to the fraction of the first isotope times the mass, and then I'm going to add that to the fraction of the second isotope times the mass times the fraction of the third isotope times the mass. And then it just keeps going on. So as many isotopes as we have, we can continue doing this. So I'm going to explain that. So putting this into context, or putting this into using numbers for this. All right. If I have element X, there's no element X on there. All right. This is just hypothetical element, whatever. And I say element X has 3 different isotopes. All right. One isotope is X12, and then we have X14, and then we have X16. So we have one version of it that has a mass of 14, one version of it that has a mass of 16, and one version of it that has a mass of 12. And through running it through a spectral analysis, we determined that 30% of the time it's X12. 60% of the time it's X14, and 10% of the time it's X16. So the way that we would use this calculation, so my isotope 1, the fraction of this, so if you remember that a percentage is just out of 100, right? So I would go,
So they give you that percent?
yes, that's going to be given. They're going to give you the percent abundance. So we have, basically we have 30 over 100, or 0.3, times the mass, and I'm going to go ahead and make it a 2 decimal places, because masses, we usually go to 2 decimal places. All right, so I'm going to take that number. That's my isotope 1. I'm going to add it to isotope 2, which is 60 over 100 times 14.00. And then isotope 3, in this case, is 10%, so 10 over 100. And then I'm going to add that together. All right. The way I'm setting this one up, I would expect my answer to be in 4 sig figs at the end, just because these are all exact numbers, and I'm telling you the masses, I want it to 2 decimal places. So my answer is going to be in that. So when I do this, when I do each of these calculations and add them up, I get 1360. All right. If you need the exact numbers for each one, 0.3 times. So just remember, so when we add this up, remember this side grows until it stops, and then you end up with a 1360 that way. So my average atomic mass of element X would be 13.6. If I had to try to figure out what that is on the periodic table, it's probably something in between carbon and nitrogen based off of that. It may be just a bad sample of nitrogen, or it may be a bad sample of carbon. All right, or an impure sample of it. But that's what we came up with. All right. So before I move off of this slide, do you understand? Does it make sense what this equation is doing? You've done things like this before. If you've ever calculated your grade average, if you've ever done anything that is a percent-based thing, like if you're trying to determine how much you need to lift based off of a percentage of your body weight or something like that. You've done these type of calculations. It's not anything new. We're just putting together to get an average mass for it. All right, so let's look at it. Let's look at it in a real problem type situation. So I just want you to understand, whenever I say fraction of the isotope, the fraction of the isotope is a percent of the natural abundance. So yesterday when we were talking about isotopes, I know on the slides that I presented, I kept using the word abundance. The abundance just means how often do we see it in nature. So 30% of the time we find X12, 60% of the time we find X14, and 10% of the time we find X16. All right. So let's look at a real element and real world. So I'm going to look at chlorine, for example, for this. All right. Oh, I'm looking at gallium first. Apparently, I switched the order of my slides. Says gallium has two naturally occurring isotopes. Gallium-69 with a mass of 68.9256 AMU and a natural abundance of 60.11%, and gallium-71 with a mass of 70.9247 and a natural abundance of 39.89. Now notice on my first example, I just used these numbers. All right. If you're given a prompt or a question that gives you an exact mass, like these did, that gives you an exact mass, that means they ran, it means they gave you they ran it through some sort of machine that gave us these exact numbers. So we're going to use those exact numbers in our calculation. Now, in this case, for our answers, when we set up the problem, our driving answer is going to be based off the fact that our percentages are 4 sig figs. So whenever we do the multiplication, our answer will have to be in 4 sig figs at that point, and then we can go from there. So let's look at how we would set this up. All right. So the first thing I'm going to do is go ahead and get the fraction of each of these. So for my fraction percent of gallium 69, it's going to be 0.6011. I'm just going to. It's 60.11%. That's a mass. This is the fraction. Percent is always the fraction. All right. So if it finishes up, that makes it make more sense. All right. So I'm trying to get the fraction of percent, just the decimal percent. All right. And then that one is that. All right. So now plugging it in, putting it in the way that we did. So I only have two isotopes this time. So I can use 0.6011 times my 689.256. And then for this one, I'm going to use my 0.3989 times 70.9247. All right, so now that looks like what we did on the last one. All right, all I did, instead of putting 60.11 over 100, I just used the decimal here, and because I like using decimals more than fractions. All right, my brain works for that better. So now I'm going to calculate both of these and see what I get. All right, so based on this, if I just do this one as it is, it should be 68.9287, 9256. So the actual number that I get 41.4321, and I'm underlining under the 4. I'm underlining under the 3 on that one. Why am I marking that 3? Because my sig figs are those numbers, those 4 sig figs based off of this. All right. So same thing here. I'm going to get 28.2919. And then I'm going to put that line under that 9 right there because that gives me my 4 sig figs. All right. So from here, I'm just going to add them together. So I add this together. And I get an unrounded number of 69. .7231, and then my final answer would be 69.72. All right. So, do you see how we got to that answer? All right. Like I said, this is not complicated. You're gonna do this as many times as isotopes they give you. So you'll do it for each one and then average them all together. Sig figs is going to be base. So each one of these you will base sig figs off of that part, and then here, since we're adding, we're going to base it off of whatever the number was or the precision was on that. So we can kind of look at that. Let me make sure I have the question I want next. Yeah. All right. So go ahead. I'm already setting this one up. So for chlorine has 2 naturally occurring isotopes. We have chlorine 35, which has an actual mass of 34.97 AMU, and it's 75.77% abundant. And then we have chlorine 37 with an actual mass of 36.97 AMU with a percent abundance of 24.23. So what I'd like for you to do is go ahead, I've already done the math for you. I need you to see if your answer matches what I have and see if we get there. The other thing is just learning regions, and it's not a difficult task. I can show you at the you're not. Are you at the match today? Yeah. I can show you the match today. When is what? There's this one, and then the DE test will be sometime next week, probably Thursday.
Can you explain? Can you help me do this calculation for the
I mean, we're going to spend time next week practicing. Yes.
I have to go.
That's right. It's 4 sig figs. So that's what did it just round up to 26.50?
Yeah, but if I'm adding this number to another number, I'd leave all of that and just know that I have to go to 2 decimal places on my answer.
Okay, I just thought you had to do sig figs after every step.
No, always do the sig figs at the very last, but recognize that that's going to be a 4 sig fig answer right there. All right. So, if you don't have it yet, continue getting your calculation. If you do have it, go ahead, check your answer up here, see if you match, and then we have a moment to ask questions. All right. Any questions about this answer?
Do you want this Max?
I don't need it. All right. So I'm gonna go ahead and talk about. So, question was asked earlier about why do I know that this answer is going to be 35.45 as far as sig figs are concerned. All right. We don't do sig figs after every step, but we have to pay attention to what they would be after every step. So in this first step, I'm doing multiplication. Here I'm multiplying a 4 sig fig number by a 4 sig fig number. So that means that my true precision stops at the 26.49. All right. These other numbers technically are just garbage that the calculator is spitting out. But whenever I add them together, just like in banking, if you're getting interest on account, you want them to start rounding those fractional pennies into your account because you don't want to lose that money. So these are all fractional pennies that we want to average in there. We don't want to lose them. So I'm technically stopping here, but I also don't want to cheat somebody else by over rounding. So I don't want to round at this point. Same thing here, a 4 sig fig number by a 4 sig number. But on that one, when I go 4 sig figs, I stop right there at the 7. All right. So I have 26.4967 plus 8.957 here, knowing that my best precision is right there at the 2 decimal places because this one can only go there. So I'm going to add it all together, and then I'll round from whatever this number is to here and get that. And so I get my 35.45 at that point. All right. But so I know that sig figs are complicated and sometimes they can be confusing, but if we just kind of take it one step at a time, it should make sense. Now, reality is you're probably going to plug all of this into a calculator at once. All right. At that point, you just need to make that verification of what it should be. How many decimal places does it have to be? Things like that. So just be careful when you do it. All right. If you're ever in doubt, maybe ask, and I will try my best to give it to you without giving away an answer. All right. I'll try my best to lead you in the right direction. All right. So what I would like for you to do right now, go into Google Classroom. There should be, in Google Classroom, you should have a Google form that says mid-class isotopes. I want to make sure. And even though it says number 4, it is a weighted average question for you to try to answer on your own. It probably won't auto grade it, but I'll use it tonight and look at it and see if I need to reteach anything or re-go over anything with it. All right. So going through here, so whenever I did my 78.7%, so I have 0.787 times 24.0, I get 18.888. Since 3 sig figs, so I know that's my precision mark on that one. The next one was 0.101 because 10.1 divided by 100 is 0.101. And then that one's going to be by 25.0. And so for there, I get 2.52 is my answer. And that 2 is my precision on that one because of 3 sig figs each. And then I got 0.112 times 26.0. And my precision on this one, 2.912. And my precision on that one is at the 1. So whenever I add all of these together, my least precise number in the addition is the one that ends in the 8 right here. So I add them all together, and I get 24.32 ... And I'm only caring about that 24.3. So if you answer 24.32, you weren't wrong. But to be sig fig precise, what it would ask for on the test, 24.3 is the best answer you can give there. All right. Questions about this? All right. If not, let's do this part. This is more the relaxing, fun part. 3, 4, 5, 6. Take one, pass it back, please. 1, 2, 3, 4. Take one, pass it back, please. 2, 3, 4, 5. Take one, pass it back, please. All right. So, like I said before, in this class, you are going to get multiple periodic tables over time. Some of them are going to have a lot of information on it. Some of them are going to have very little information on it. It's just relating to what I want us to know at that particular time. So I am never going to do like Dr. Wilson did to me when I was in high school in this room. I'm never going to do what he did to me and give you a blank periodic table and say fill it out from memory. All right, that is not what I'm asking you to do. So what I'm asking you to do is I want to start identifying regions, and we want to start breaking this down into meaningful parts of the periodic table. So there are 3 major categories of it. I'm going to give you the notes on it first, and then we're going to talk about how we're going to color this. All right. So there are 3 major categories of elements on the periodic table. They are broken down into metals. What did I just do? They're broken down into metals. And so when we locate these on the periodic table, that bold line that I highlighted yesterday on there, the staircase, it kind of looks like a staircase. Everything to the left side of that staircase is considered to be a metal. All right. The non-metals is the second main category. And that's going to be everything to the right side of that bolded staircase. And if you're looking at your reference table, you can see that bold line that starts right around boron. That's what I'm talking about when I say the staircase. All right. And then the third category is called the metalloids. And metalloids are the elements that touch the staircase. Another name for metalloids that you'll sometimes see is called a semi-metal. Because so those particular things kind of act like both metals and non-metals at the same time, just depending on temperature and things like that. So what I want to do first is I want to take a minute and describe what each of these things are. And then we'll look at it in terms of the periodic table and make sure we understand where everything is. All right. So first one I want to talk about is the metals. All right. The metals make up the majority of the periodic table. They're the most abundant type of element that we found on the planet. All right. The metals, for the most part, are solid at room temperature, with the exception of mercury. Mercury is the only metal that mercury and gallium, sometimes gallium, because gallium's got a really low melting point as well. But the majority of the time, when we dig these up, we're going to dig them up in solid form. All right. Metals tend to be shiny. Another way to say that is they have luster. All right. Luster is just the fancy word for being shiny. They are malleable. Malleable means that you can take a hammer and beat them into shape. Ductile is another defining characteristic of metals. Ductile means that you can kind of pull them and draw them into wire. You can kind of stretch it to some degree. And then they tend to be good conductors of heat and electricity. So those are characteristics of metals. And then as we were talking about forming ions yesterday, the metals on the periodic table tend to form the cations. So metals tend to lose their electrons to form the cations. So they're going to give away their outermost electrons so that their inner shells are already full. And because they're giving away electrons, they form a positive ion. All right. You might need more time on this one. Okay. So the next category that I'm going to go through is the characteristics of nonmetals. Nonmetals, they're not necessarily the opposite of metals, so I don't want you to think of them like that. They just have different characteristics. And some of the things about nonmetals is nonmetals are really, they're kind of undefined because they can have a lot of things going on with them. All right. So for a nonmetal, as far as phase, we find nonmetals in all three phases: solid, liquid, and gas. So we can't really make a presumption of what are they going to be in nature. There's a good bit of them that are gas. There's a few that are solid. There's at least one that shows up as a liquid. So we can't really use that as a defining way to look at them. So some examples of solids would be carbon, sulfur, and iodine. Liquid is bromine. Gas example would be like oxygen, neon, fluorine, and all of the noble gases. All right. They are considered to be allotropes because some of these things, especially nitrogen and oxygen, can have different forms of the same element. So we can have, in nature, we can find O2, which is the oxygen we breathe, that we get in our bloodstream and all of that. And then we have O3, which is ozone, that's found in the upper atmosphere and all of that, and protects from ultraviolet, filters out some of the ultraviolet radiation coming from the sun. Same thing with nitrogen. You can have N2 and N3. I don't know the specific names of each of those, but they are found that way in nature as well. And so when you have a different version of the same element, it's called an allotrope. For the most part, really with the exception of carbon, because carbon can make a shiny surface at times, shiny reflective surface at times. Like if you've ever really looked at when you take a graphite pen, when you take a mechanical pencil or a pencil and you write on there and it leaves the graphite trail, if you look at it, sometimes you'll notice it's a little bit shiny, reflects sunlight, but it's not super shiny. So we consider them to be dull or lackluster. And then when they are solid, they tend to be brittle. Again, this is a generalization. Not all of them get that way, because when carbon is in diamond forms, it's one of the hardest substances that we know of. So, but if you hit it at the right point, it'll just shatter. So, and then in general, nonmetals tend to be poor conductors. Now, so metals tend to form cations. Nonmetals tend to form anions. So they tend to form negative ions. Or an anion. And so the way that they do that is by gaining electrons. All right. All right. Last category is the metalloids. As I said before, metalloids are also known as semimetals. These are the ones that appear along the stair-step line, but metalloids, for the most part, all tend to be solids at room temperature. They're one of the main things that we use to make semiconductors. So microprocessors, things like that. That's one of the areas, because by manipulating their temperature, we can manipulate their conductivity at the most basic level of it. All right. They have varying properties that can be metallic and non-metallic, or non-metallic at the same time. So silicon, one of number 14 on the periodic table, it's really interesting different ways that we can manipulate that, depending on what we need to do. So, glass is made from basic melting sand. Sand is primarily silicon. And so whenever we melt it and reform it in that structure, it has properties that it has at a really pretty high specific heat. So that means glass can hold heat and hold it pretty well. It makes it a good insulator. But manipulating silicon another way, we can make microprocessors and chips out of it and process electricity by manipulating the temperature again as well. So, and so those properties of it being both an insulator and a conductor at the same time, depending on the circumstance, allows us to use them in ways that you might not expect. All right. So the blank periodic table that I gave you, what I want us to be able to do on this. All right. Now, this one has a little bit more information on it than we actually need. I'm gonna start identifying the regions, and so going through here, first thing I'm gonna identify the stair-step line that I keep talking about runs. All right, and then you have a couple of more. That rows down there is complete. All right, that's not complete on this one. All right, but that stair-step line is what I just highlighted in white. So on yours, you can just bold it by kind of pushing it in or whatever. And those elements in purple are your metalloids. So what I'm going to ask you to do is either by coloring it using colored pencils, markers from up there, or whatever, I want you to identify your metalloids as those things in purple. You don't necessarily have to write the elements in. And I would recommend you getting 3 colors. You don't have to use necessarily the ones that I say, just so long as you identify each group as what it is. All right. All right, so the next grouping is everything that I just put in this blue circle. Those are our metals. All right, so everything in that large blue circle represents and so notice on your periodic table there's a gap where there's a star and a double star. I want to point this out just because we don't always think about it this way because we always show the periodic table like it is. But in reality, the expected shape of the table matches more of this. All right, so those 2 rows that are pulled out at the bottom, these 2 rows actually fit right here. So the table is actually more shaped like this. The reason why they show it like they show it is a publisher's choice so that they can fit it on an 8.5 by 11 sheet, which is the standard size for a textbook, and not have to have a fold-out page. All right. And then the other region, everything left over, everything over here to the right are your non-metals. If you want to just color your non-metals like a green or something like that, you might be able to do that. So I'm going to give you time if you want to shade in your periodic table, however, so that you can do that. Don't worry about filling in numbers or letters or anything like that, because I don't want you to have to do 118 different things on that. Just kind of get the generic regions of metal, non-metal, and metalloid. And that's where I'm going to stop the notes today.